again, I have a tremendous honor and pleasure to introduce a legend, a friend. He built some of the first super insulated houses anywhere in the world. He went to MIT, so no more jokes for me on MIT. I met Mark at the same time at the same conference that I met Betsy. And my relationship with Mark is interesting. And my relationship with Betsy is even more interesting. But we've literally known each other forever, and I view him as one of the pioneers of high performance buildings, technology, everything to do with durability, indoor air quality, and it would be sure nice to have his views on shed some light on daylight. Okay, thank you.
So you know those situations where you know that you've got the low bidder? So yesterday, you listened to an engineer with a 36-inch bar. My chainsaw has a 16-inch bar. Yesterday, you listened to an engineer with a powder blue suit. The Coen brothers have a movie about a guy like that, by the way. I actually brought a decent shirt to wear for this, but I got spilled something on it already. Low bidder. What I've been trying to do, this is the third year in a row, is talk about things that are fundamentals. And the reason I'm focused on fundamentals is I think that the combination of incentive and subsidy programs and certification programs, both of which have generated a lot of good buildings and some not so good, but a lot of good buildings. They have focused people on what teachers call designing to the test. I'm designing to the subsidy, I'm designing to the certification. I once had a client who wanted me to help him with mechanicals on a bunch of affordable housing. And I said, you need to duct this system, not use a single cassette for an apartment. And he said, I can't afford to do that. I'm at the limit of my budget. And I said, well, you don't need a Zender in a one-bedroom apartment. You could do this with a Panasonic. You'll save $2,000 at least. I love Zender, got it in my house, but you save at least $2,000 and you can buy the little ducted unit. He said, can't do that. I'm right on the limit for my passive house. In other words, I can't take 3% less efficiency on the ERV to do what actually makes sense for the building. So I think part of what's going on in our profession, in the course of making really good buildings, we have stopped asking the question, what is the best building we can build for the budget, program, occupants, location? We are asking the question, to be really crass, how do we get that LEED credit? A lot of bike racks. And I'm a cyclist, so I'm good with the bike rack thing. I once was part of a project which I got fired from at MIT, and I listened to a presentation from a very prominent passive house consultant. For 3 hours, the MIT wanted a passive house certification and a LEED certification, and never once was there any discussion about making a good building. For 3 hours. So I think some of the fundamentals of what we're doing are worth still understanding and asking the question, how do we make the best building we can with what they've given us to work with, is a place to start, not the certification. I have 2 projects that have won ASHRAE National Tech Awards and 4 that have been on the AIA's top 10 environmental buildings. And I'm not sure, except for the Kern building, which is a Living Building Challenge building, I don't think any of them are certified. But if they are certified, I think one's a platinum LEED. We never were talking with the LEED person. during design. That was a bookkeeping job. If we do a good building, we'll get enough points in LEED. The lead person wasn't driving the design process. Okay. Joe, I submitted an abstract to Joe saying, I want to talk about the fundamentals of solar energy, and Joe wrote in the program, we're going to talk about daylighting. They're related, so I'm going to do a half and half, which I like in my coffee too. All right, so the famous Andy Shapiro question, which we always ask, why bother? Why do we care about this? And so I have a number of reasons. I'm going to assume you can read. Most of us are old enough that we didn't go to school recently. Lots of reasons to understand how the sun works and how we apply it in buildings. So where do we start? The Earth's axis is tilted at 23.45 degrees. It's always important to use a lot of decimal points if you're not sure of something. And by the way, Eva's presentation, which was awesome, you notice there were a lot of really big words? Well, I've been a consultant longer than Eva, I can tell you that. And it's important to be billable by syllable. You never use a short word when a long one will do. Okay, so the tilted axis of the Earth is what gives us seasons. And in the summer, we're tilted towards the sun if we're in the northern hemisphere. If you're an Australian or from New Zealand, you're screwed today with this, so stand on your heads and it will make sense. And then in the winter, the sun's way lower, we get less of it. And these are sun paths, northern hemisphere. So when people say the sun rises in the east, that's only partially true. In the summer, it rises in the northeast. In the winter, it rises in the southeast because the sun paths are shorter. The sun is lower in the winter. So far, people with me? I mean, some of you people have been outdoors before? Okay. So what do we get from the sun besides sunburns? This is the solar radiation spectrum, and you'll notice that 42% of it is visible light, and that's for humans, right? Because different species have a different range of what they can see in. But we're talking mostly about humans today. As Eva pointed out, there are many other occupants of our buildings, but they never pay the frickin' mortgage or the rent, so we want them out of there. 53% is infrared, 5% is UV. And the gray line is what hits the Earth above the atmosphere, and then water vapor and stuff in the atmosphere absorbs some of that radiation, and what hits the planet's surface is lower by about 30% lower. Again, so far with me? Glass. So let's talk about how the glass interacts with the solar spectrum. The top line, these are all lines on the left, 0 to 90% is transmission, and on the bottom is wavelength in nanometers. Nano is a very small word. So the top line is clear glass, right? And clear glass gives you the most visible light, and it doesn't cut off a lot of infrared. And then we invented low E, and the top low E here is 189, which is the hard coat low E, that cardinal, these are all cardinal numbers that are on the inside of the glazing and has some benefits and some drawbacks. Won't go into that today. Then we're talking about the next ones are all in a double glazed assembly with the low E coating on one of the two inner surfaces. So low E 180 is Cardinal's high transmission, passive solar, low E, and you can see it gives you a fair amount in the infrared. And then we go to the selective emissivity glazings, low E 272, and all of a sudden that curve drops dramatically in the infrared. So it's selective. It's designed to emit visible light as much as possible, but exclude a lot of the sun's heat. And then you can keep going down and you get to like low E cubed 366. That's That's the Phoenix and Florida glazing. And one of the interesting things is in some jobs that I'm working with architects, and they get a window order submitted, a window proposal submitted from one of the window vendors, I'm seeing this starting to pop up in the Northeast, 366. And I don't really need 366 unless I put in way too much glass. And way too much glass is like way too much ventilation there. It's not good. Let's look at solar heat gain coefficient, how much energy of the sun actually gets in versus visible light transmittance for some of these glazings. And if you look at the solar heat gain coefficient and the visible light transmittance of clear glass, those two numbers are about the same. This is Mark's sloppy math, which actually precedes Joe math by a few years, because I'm a little older. So the solar heat gain coefficient, double glass, 76%, visible light transmittant, 81%. And then as you go down into the selective emissivity glazings, what happens is you're cutting the solar heat gain coefficient much faster than visible light transmittance. One of the things about humans in buildings is that you don't want to cut down VLT below a certain level where you start getting internal reflections. The glass is mirror-like. So at night, we expect that. You know, it's pitch black outside, you look at a window, and you see a reflection. But if you get the VLT down too low in glass during the day, you start to see reflections. So I have kind of an arbitrary number, 50%. I don't ever want to go below 50% VLT. With conventional glazings, that's not a problem. It's something I've seen more in my bigger institutional projects that I have managed to squash over the years. So how do you calculate how much solar radiation you're going to get? The first thing I want to say is you have to distinguish between clear day insolation and average day. And the reason I'm making this point is most modeling software is average day, because that's how you're going to tell how the building performs through the year, average month by average month. But there's a lot of things that doesn't tell you. Clear day, of course, we're using in a cooling load calculation because we're looking at clear day. Now, it's true that actually no one is doing cooling load calculations, but if you did do them, you would care about what a clear day amount of insulation is rather than an average day. Anyone here who's reviewing people's manual J's know, or even engineers, that you do the calculation, double it, and that's the system size. Clear day data is also used if you want to do anything with solar energy that is not in your modeling software. You have to understand that it's clear day that you need. So if you're sizing thermal storage, if you're sizing electrical storage for PVs, if you're sizing blowers and pumps to move energy around from the sun, you have to understand what happens on the clear day rather than the average day. So here's an example of that. This is an art barn in West Tisbury, Massachusetts. And I'm going to talk first about the little greenhouse. The owner wanted a place to start plants and a place to overwinter, because she's a seasonal resident, all the house plants in the other buildings. And she didn't want a heating system in this building. And she said, and I don't want the building to go below, the greenhouse to go below 50 in the winter. So with a greenhouse with all that glass, you have to take excess heat out of the greenhouse or the plants fry. By the way, one of our front row people here once, a long time ago, wrote a book, a pretty 40 years, a pretty definitive book on solar greenhouses. Is it in print, Andy?
No, but you can get one for $3 on Amazon.
So you can get one for $3 on Amazon. So we decided to take that solar energy, instead of blowing it outside, blow it down in the little basement below this greenhouse, and store some energy and water. And you can see the duct, you can see the duct here going down the stairs. It takes, when, there's a thermostat, and then when it gets to 80 or something, the fan turns on. And then the basement, you can see the duct, and the fan is here in line. And then you can see a lot of racks with water containers, 5-gallon water containers. And you can see the little branch ducts going to the wooden manifolds. So I need peak hourly insulation to size the blower. How much energy do I have to move out of that greenhouse? And I've got two different orientations. I've got sloped and vertical. I need peak hourly clear day insulation to size the heat transfer I need from the air to the water containers, which is kind of a tricky thing. Rock beds are really easy because they have a lot of surface area, but there were a lot of reasons we didn't want a rock bed here. So we had to store it in water, and that's tricky. Getting air energy, airborne energy into water is a little bit tricky, but I need clear hourly data for that. And then I need daily clear data to size the storage. And if I say stuff that doesn't make sense, ask me, stop me.
I got a question.
Yeah,
What is insolation?
solar radiation. Billable by syllable, dude.
Yeah, right.
If I just say sun, I'm gonna get paid way less. Okay, so these water containers are in racks of 15. The manifolds are drilled with a bunch of holes, and we're sending pretty high-speed air through these little jets, because at a certain velocity, you wipe off the surface layer of air and you transfer heat into the water. And of course, we put, I'm a compulsive measurer, so we had, data collection in the water to measure the temperature going up. And this is a cool rig with a little Fantech fan and an iris damper to test the engineering calculations to see if what they told me at MIT actually works. And it was unbelievable how close the numbers actually worked out. That's just for the geeks around here. Kent, that one was for you. All right, so where do I get the data? Well, one place that's free and very easily available is PV Watts. It's an NREL piece of software, and it's made to model solar electric system performance. And here's my little PV system on my house. It's a little under 5 kilowatts. And I enter, first of all, where I am. So you see my zip code there. Change location. I'm not going to Houston, so I'm staying right where I am. System size, the module type, which is basically efficiency, the array type. It wasn't broke, so I used the fixed roof mount. The system losses, there's some issues about how you calculate that. And then the two things here, the roof tilt, 30 degrees, and the azimuth, which is a multi-syllable word, or which way is a point, right? So my house is 11 degrees east of true south, so the azimuth is 169. True south would be 180. Now there's a lot of different pieces of software. Some use 0 for south and some use 180. That kind of sucks if there's no real convention. So you have to understand your software or you'll get really bad results, because unless you're in Australia, north facing is not a big gainer. Okay? Now, once I measured the surface temperature of my triple glazed windows in my house on a cold outdoor day, it was freezing, about 30. And the inside temperature of the glass was over 100 degrees. That was kind of interesting. So then I thought, well, I'm going to measure the north side glass. It was a day where there was actually snow on the deck, so there was a fair amount of diffuse radiation hitting that snow, and the temperature of the north-facing window on the inside was warmer than the air temperature in the house. So when you have really good glass that has very low heat loss, even with very low solar gain, you can have a net gain. The snow is what made the difference. All of a sudden, I have a super reflective surface. That's extra credit. Okay, so you run this, and what PV Watts is telling you is for every month, what is the average day insolation on that array? And then it converts it to kilowatt hours a year because it's a PV program. My long-term experience and gut is that it slightly overestimates these numbers. Now, why is that true? I have no idea, but these pieces of software are taking what is almost always horizontal measurements of insolation. That's where the data is usually taken. And then there are algorithms that convert it to what angle the surface is on and how much diffuse light is coming from the sky and how much reflected light is coming from the ground. So different models of that give you different answers. And they're not super different, like no one's building is gonna fail because they use this model versus that model. But they will be different. If you run two different pieces of estimating software, they'll be different. And by the way, when I have looked at data from my PV system, which is rated at 4.76 kilowatts, you'll never see 4.76 kilowatts out of that system. Like if it was in Barstow, California, you might. I have seen 5 kilowatts out of this system. When? Cold weather, perfectly clear beam radiation hitting the array, and a bunch of clouds in the sky that are being fully illuminated by the sun. So the clouds being really bright in that condition are adding gain to that array. That happens about once a decade. All right, but you can, even though it's made to model PVs, you can use this to model what comes in through your windows, or hits your windows, excuse me. So I changed the tilt to 90 degrees because I'm not an architect. I put windows vertically. Frank Gehry. And then I get the results of what hits that south-facing window, or in my case, 11 degrees east of south. And you can see that that number's lower, right? 915 kilowatt hours a year. I did it for 1 kilowatt. Let's maybe look at the bottom number. For the annual average is 3.4 kilowatt hours per square meter per day. And on the slope surface, it's 4.97. So it's 70% of the, 2/3 of the annual insolation hits a vertical window versus a sloped 30-degree roof. So I can use PV Watts for all my energy modeling calculations wherever I am. And I paid for that with what are called taxes. That's a word that's going to soon go away unless you are worth at least $1 billion in the United States. Okay, here's another one. I wonder, any of you Seattleites, do you know Christopher Gronbeck? Yes, anyone? Yeah, so Christopher Gronbeck is an old friend of mine and a super smart guy, and he has all these calculating tools, again, free online, although he has a tip jar. And so once a year, I probably put like a $20 tip into Christopher's thing because he's maintained this for years. By the way, my presentation is completely available, both as a PDF and as PowerPoint. So we're gonna look at a couple of these in this presentation. This is the window heat gain. And I can't imagine that you can see it because I can't read it from here, but I get to choose my location and I get to, and it will then tell me by month what the average clearness, is by month for that location. So I picked Boston because we're close to that. And you can see in December, it's 52%, and in August and July, it's 65%. So that's at least it's kind of making evident what some of the data, base data inputs are. And then I picked my ground reflectance, and I picked my window solar heat gain coefficient and the orientation, and I got the output in kilowatt hours per square meter. And then I get this cool table by month and by hour. And he even tells you which hours are morning and which are afternoon.
But it's all average.
It's all average because that's what I asked for. But if you waited 10 seconds, you'll see that you could click on clear day link, and now all those clearness numbers go to 100%, which means it's all clear. Are we all clear on that, Andy? A little hazy, yeah. Hey, at your age, you're still in the front row, man. And then the table comes out and the numbers are higher. I bet most of you, it's a homework problem, figuring out why the numbers are higher on a clear day, okay? All right. So I use this tool as well. Let's look at how much insolation is on various surfaces on Martha's Vineyard. So I picked southeast, north, and west, and 45-degree roof. And the red line is a 45-degree roof, and so you get a lot more sun on a sloped surface, and that's because the sun is neither perfectly horizontal or perfectly vertical when you're at 41 degrees latitude, which is Martha's Vineyard. We're at 42 here in Westford. And then the bottom purple one is north. You get the least amount of sun on the north. It peaks in the summer, as do the two middle ones, the light blue, turquoise, and the yellow, east and west. So east and west peak in the summer. That's why you don't want to have a lot of east and west glass in a building. You're just buying cooling load. And then the green one that looks like the duck curve, because we're trying to keep that wildlife, motif going on here, that's the south. And so that's why we want buildings to face south when we design passive houses and things that even aren't passive houses. They get more insulation on the south glass in the winter than they do in the summer. Matching the load that you're trying to serve to the tilt and the azimuth. So the first question is the load seasonal or is it annual? Heating is a seasonal load, unless you live in Duluth. Mike LeBeau isn't here this year. Pool heating, I'm thinking about, when I say pools, I'm talking about outdoor pools, is seasonal because most people don't even try to heat their pools in December. Those are seasonal loads. Electricity use, domestic hot water, those are annual loads. So how we understand the loads has to do with how we want our solar collector, whatever it is, to face, whether it's a window or a PV panel or a pool collector. Is the occupancy seasonal? So when I see schools with solar hot water systems on them and the schools are unoccupied during the highest insolation months, that seems to me like maybe you should have spent the money somewhere else. Is the system output exportable? Well, the only thing that's really exportable on a per building basis is electricity. In a district system for district heating, that energy is exportable depending on how the system's designed. But really for most of us, the kind of buildings we're working on, only electricity is exportable. Now, what about where your building is? This is month by month, kilowatt hours per square meter per day, average radiation on a south-facing surface. Barstow, California, the red line, it really wins. It's hot in Barstow, and it's also very dry. The purple line is Seattle. And French was already used today, so I'm going to say, c'est dommage, Seattle. Seattle does not get a lot of sun in the winter. This is why there are a lot of depressed people in Seattle and a lot of coffee being sold, right? Boston is the blue line, and Boston is not so bad. Look at Boston, January, February, March, go Sox, right? We actually have a fair amount of radiation in the winter. The most interesting curve on this to me is Austin, right? So I picked Austin because I think, well, Texas, it's always hot and sunny, it's freaking hot. Look at Austin. Austin actually is below Boston in the later winter and slightly above Boston in the late fall and early winter, and it's the lowest in the summer. Now, pop quiz. Why is Austin lower than Boston in the summer on a south-facing window? I think we have a winner here. So Boston's 42 north latitude. Austin is 30. That's 12 degrees difference. The sun's higher in the sky, right? So the window that it sees, the slice of sun the window sees is lower. Thank you. All right, matching the aperture to the load. Now we're going to talk a little bit about some of the mistakes of the passive solar movement. This is my house, which is actually sort of L-shaped. You can't see the little north L. It was an existing house. We gutted it, put way too much money into it, and made it into a pretty nice little house. 11 degrees east of south. There's 110 square feet of net glass. The house is about 1,200 square feet of net floor area, 1 story over a basement. Let's distinguish between average and peak, clear day insolation. So the January net heating load for this building is about 5 million. By the way, James was showing us data from passive houses where he showed us in actual was around 5 kBDU per square foot per year in heating. Something's wrong with those buildings. Like Galen's experience is different. My house with a huge amount of surface to floor area ratio is a little more than half that, and it's not a passive house. So I would look at those buildings carefully to figure out why it's 5. My net heating load's about 5 million. My average daily January insolation is that number. So if I just said I want it to be 100% solar heated in January, that's easy. I divide 953 times 31 days in January into 5 million. I look at my glazing solar heat gain coefficient. It's triple glazed with cardinal low E on 2 surfaces. The big windows that are fixed are low iron glass on the outside to really bump the solar heat gain coefficient and make them more expensive. So I need 282 square feet, and that will be just 0. That's just all the energy comes in an average year will offset my heating load. But wait, there's less. The clear day insolation is almost double that. The average daytime heating load, 8 hours, is about 44,000 BTUs. If I put 282,000 square feet of glass in there, the clear day solar gain is almost 300,000 BTUs. The net gain is 250,000 BTUs. This is a big number for a little house. With sort of standard thermal mass of construction, which we studied last year, this will be on the test. The house would go up about 34 degrees. Then you could say, oh, it's like one of those old passive solar houses. So that is bad. So there's this concept of utilizability. How much of that heat can you really use? Because each square foot of marginal added glass gets you less usable energy. Utilizable is more syllables. So I say utilizable. But each additional square foot of glass has the same amount of heat loss. So you're on what's called the diminishing returns curve. And the actual glazing area is still somewhat overglazed. So if you are old and you learned in the passive solar days about sun tempering, there was a guideline which was 8% south plaster floor area, and I think that's still too high for the low load buildings we're building today. But I did it anyways because, James, you are not the only one that can quote really cool old dead people. So you had something from David Hume, but I am going to quote Carl Jung, so I up you. Intellect is a fly speck on a sea of emotion. I wanted the glass. All right, overhangs. How do we shade south-facing windows? Well, time-honored is overhangs, and you can see the sun high in the sky in the summer and low in the sky in the winter, and then some middle of the seasons, close to the equinoxes, the sun's in the middle. What a coincidence. We can go all the way back to that second slide. So what do we want from our overhangs? Well, in the heating season, I don't want to block direct sun. In the cooling season, I'd like to block direct sun, but it's really hard because April 21st and August 21st have the same sun path, and they actually have different climates and temperatures and stuff like that. So it's not easy. As the azimuth diverges from true south, and the building is not facing south, the overhangs you need to shade it get longer and longer and longer. And in the south, they used to call those porches, okay? But there's some disadvantages of shading it permanently and deliberately, because when you put a porch on the side of the building, you have no access to the sky dome for daylighting, and we'll get to that. All right, overhang terminology. It's not just the depth of the overhang and the window height. A key number is the separation distance. So you're really looking at a ratio of X over D when you design overhangs. And the bigger the overhang, if you want to get what I said, summer shading and winter penetration, as the overhang gets bigger, the separation distance has to get bigger too. And that's actually, in a house, it's sort of an architectural problem because the houses start to look weird if you really do the overhangs very rigorously. That's my opinion. So I'm going back to Chris Gronbeck. He has this amazingly cool overhang calculator, and you can set where you are, what the window is, what the overhang is, and all these things are sliders. And as you slide it, if you see that picture of the window where the shade is just above the window, the shading, if you slide it, the shading moves across the window. It's like real time. It's a great tool. It's so brilliant. And then he'll give you the same kind of big table, and it's kind of color-coded according to how much shading you actually get. And then you can ask for different outputs depending on how you've specified the window. All right, I have 2 slides on solar pool heating. I'm not a big fan of solar pool heating. Pool collectors are typically unglazed plastic absorbers. Guideline in the Northeast, you need 50 to 100% of the pool surface to heat a pool here. You have to find a place to put that. So if you've got a 20 by 40 pool, now you're talking about 400 to 800 square feet of collector that has to go somewhere. It could go right over the pool surface, in which case you would suppress evaporation, but swimming would be harder. So the most important thing to do to a pool is you got to cover it when you're not using it, because most of the heat loss, energy loss, is evaporation. My opinion, which could be debated over beer, is that it makes much more sense to use solar electric panels with a heat pump pool heater than it does to use thermal energy, because the excess energy can be exported, and heat pump pool heaters, because they're working off of pretty warm outdoor air when you're trying to heat a pool, they're working at COPs of 5 or more, the best ones. So they're pretty efficient. And here's a model for a pool in Boston, outdoor pool, with and without a pool cover. And you can see that if in the real summer months, June, July, August, you don't even need heat, because water is a really good solar collector. absorber, right? So the energy comes in and then you cover it at night or if you have a transparent pool cover, you don't really even need heat typically in a pool if you've got a good pool cover. All right, daylighting. So now I'm going to actually do what Joe asked me to do. So this is my definition. I'm sure there are better ones. It's the controlled admission of natural light from the sun and the sky to provide building occupants with the lighting needed to perform desired tasks. So that's important because you have to think about the occupants if you're talking about daylighting. Daylighting may save energy. It does not always save energy. It actually has to be done really carefully to save energy. However, daylighting has multiple beneficial effects on humans, and so we like daylighting. But if you do it really well, you can go beyond energy and being able to see and all that stuff, and you can make people feel really great in a building. And my favorite building on the whole planet, and I have been in the Taj, I have been in Hagia Sophia, I have been in the Pantheon, these wonderful buildings, monasteries in Japan. This is my favorite. Saarinen, 1954. It's the MIT chapel. My younger sister got married here. This cylinder is in a moat, and the moat in the non-freezing season is filled with water. And then these little arches around have glass up at the top. And so if you are lucky on a sunny day in the right season and you are in the MIT chapel, the light bounces off of the moat up on the inside walls. It is an incredibly sublime space. And then there's one skylight, which is the only other glazing with this amazing sculpture below it. And that's the lighting in the space. It is just a fabulous building, and you're not that far from it. You could go see it. Okay, let's talk about saving energy with daylighting. If you use daylighting and you want to save energy, you've got to control electric lighting. You don't save anything if the lights are still on. These days, you can buy light fixtures with dimming ballasts and the sensors built in about the lighting, and each lighting fixture can individually dim. This, from when I was really doing this work, this is way better than what we had before. The proper analysis of daylight savings, however, have to include the energy used for heating and cooling. You've got to look at the energy that the glazing is causing you in your space conditioning, as well as what it saves of your lighting. If you look at lighting efficiency in terms of light output, lumens of light per watt, LPW, a foot candle is 1 lumen per square foot. And what's changed over my career is that lights got way more efficient. So incandescent to fluorescent to compact fluorescent to LEDs, we've gotten way more efficient light. The lights, the actual light lasts a long time, and they're very efficient. The sad fact is that LEDs can provide light with less cooling load than sunlight. And that's if you did a really good job of daylighting. You do a crappy job of daylighting, game over before you even start. So my advice to people is you optimally do daylighting with the glazing that you really need for other purposes, and you're careful to not overglaze a building, or at least you know what you're doing when you overglaze the building. Particularly with south-facing glass, because too much south-facing glass can actually shift so you have a cooling peak load in the late fall. All right, let's talk about lighting and why we have lighting in buildings, and we're getting back to humans once again. It's so boring. Good lighting helps us put our attention to what in our visual field is important to us. And I think there's two ways to think about it. There's two things that make this up. One is very clearly functional to perform task. But the second is because we are animals fundamentally, and we have some basic needs. We want to know where we are in time and space. This room's a great example of, like, what is it doing outdoors? Where are we on the planet? We have no idea, right? And then safety and security. You know, we're always looking to see where we can be a predator, or more importantly, where we have become prey, right? So these are not conscious, unless you're paranoid. So, you know, and just because you're paranoid doesn't mean they're not out to get you. These are our needs as animals, as people. So lighting, I think, does both things. And the bottom line is, in our visual field, we are confronted with huge amounts of stimuli, and our brain is what actually makes perception. So there's sensation, but then perception is our brain sorting what's important to us from all the other garbage that we don't need to pay attention to. So we want to focus on thinking about lighting what's important to us. Another quote, see, James, engineers can do this shit. Perception thus differs from sensation by the consciousness of farther facts associated with the object of the sensation. William James, one of the early people who really studied what perception is. Okay, how do I know some of this stuff? Well, I am totally not a daylighting expert, as you will completely understand by the end of this presentation. But these are the two best books, I think, ever written on this. William Lamb, in both cases, Bill Lamb, Perception and Lighting as Form Givers for Architecture. And he goes through, in the beginning particularly, what are we trying to do? Why does it matter? How do humans see? What is perception? It's just a masterful piece of work. Chris Whitman was the editor of this, another great lighting designer. And then Sun Lighting as Form Giver for Architecture, his second book. And the reason this is an important book, and this book is filled with little models and testing of different configuration, all different kind of configurations of lighting, is that I showed you that Saarinen building. The history of daylighting, really, in modern times, comes from cloudy Northern European climates. Saarinen, Aalto, a bunch of the Brits. And Lamb realized, well, you know, it's cloudy sometimes in America, but by God, there's a lot of sunlight here too. And so you've got to think about both. It actually, the daylighting problem got harder, not easier, being here versus Finland. And the names got easier to spell. So what are some basic daylight? By the way, I don't have a time check on this, at least that I can read. Where am I in the, all right, I'm doing fine then, thank you. All right, basic daylighting principles. Avoid glare. Glare, you can't see. If you're old and you drive at night, you know a lot about glare, right? It's good, it's not a magic rule, but it's good to provide light from more than one direction. Christopher Alexander, among many design patterns. Avoid beam sunlight, direct sunlight on whatever the work plane is. So whether that's a monitor or a desk or a piece of machinery in a factory, lighting something where it goes from 500-foot candles to 10 as a cloud passes does not let you see what you need to see. So direct beam lighting wants to be excluded from the work plane. Minimize contrast between objects. So you don't want to see something super bright next to something that's dark, because your eye is working really hard to make sense of that, and your pupils don't know whether they're supposed to be open or closed or whatever. Use reflective surfaces, light surfaces, to move light around inside spaces. provide views to outdoors. That's why we have windows. Oops. And then you have to give occupants control over daylighting sources that could put beam lighting in their eyes or on the work plane, or they'll be unhappy. Not daylighting. So the second story of this grocery store is where the offices are, and you see what the occupants have done. And once this is like this, it's never removed, right? Because it's sort of, no one can be bothered to like up and down and up and down, so they just block it off. This was not the photo that the architect put in the AIA prize submission category. All right, let's talk about reducing contrast. So this is the interior of our house before we accumulated too much shit. And you see those big south windows, and you see the framing between them. It's a big difference if that framing was wood, was dark, right? So what you can see is there's a hierarchy that's workable for your eye to go from the window to the framing, the side of the window opening, to the other surfaces. And that contrast gradient is what helps you see. In the other photo, this is a deep wall, this is a double stud wall, and because it's a narrow window, the sides of the window opening are splayed, and you have some of those in your house. You kind of need a fat wall to even make it worthwhile to do. Reflective surfaces, so this is one of the back rooms in my house. The glass is pushed right up against the party wall to the other bedroom. And you can see the effect of and these are north-facing windows. So you can see the effect of lighting the plaster, and plaster is so much better than drywall for this, because this texture in the plaster, it's not just this flat surface, right? You do it with straw bale, but you know, if I retrofitted this house with straw bales on the inside, I'd have to be crawling around. So, you know, I just didn't do it. On the right-hand side is an office, in a little office building. This was the first certified LEED building in New England. I had to throw it in for Chris. Go LEED. And I'm going to show you the daylighting model later on, but what's the usual move? The usual move is this is a double casement pushed together, right? That's the cheaper way. There's fewer only half as number of rough openings. Instead, push it against the wall and you get that reflection. Different climates have different, we know, heating and cooling domination. So where are you doing daylighting? Is it a hot climate? Is it a cold climate? Is it a sunny climate? Is it an overcast climate? The strategies depend on climate. They're very climate dependent. If you've traveled in, like sort of Arab Africa, you see these buildings that are courtyard focused. And like from the outside, you don't even know whether it's a building or a wall, right? And all the openings are on the inside, and it's just to exclude the sun in this brutally hot environment. So people have evolved vernacular solutions to the climates that they're in. We would rather just make buildings all glass and give ourselves awards. Cloudy climates rely on the whole sky dome for light rather than just the sun. So that's a key difference that you have to think about is, can the glazing I'm putting in see the sky dome as opposed to where the sun is tracking? And I've already said this, so I'll skip it. So let's talk about different places where glazing can be put. Side lighting is very dependent on orientation. We learned that in terms of how much sun comes in. North and south are optimal. North, because in general, you don't need much lighting control because the sun isn't on a north window for very long in a whole year. And then south, because you need the least amount of overhang or control on south. And I think I've already said that. So a guideline, if you're side lighting with windows, your penetration of the daylight zone is going to be about 1.5 times the head height of the windows. And so when you go into old buildings, you often see that the ceiling heights are higher and the glazing goes way up. And there is a great building. Andy and I, over the years, have done different kinds of forensics and this and that in old buildings in the North Country. The Woodstock, Vermont courthouse has 2 really cool things. If you go into the main room, the corners in the ceiling have big grates, and that's ventilation. And then you go in the attic, and there are wooden ducts from the 4 corners that go up into the cupola. And you found that library was in Virgins, was something similar. So they had ventilation, and then the windows are full height in this double height space, and the shutters are 3 level. So you could close the shutter that's going to put direct sun to your eyeballs while leaving the glass open up there. And how do we design most shades? We pull them down from the top. Not a good idea. Pull them up from the bottom. Better idea. So we can, on side lighting, we can control sunlight with things that are either fixed architectural features or operable, and they can be inside or outside. And operability can be automated or manual. If you do a really bad job on the automation, then they will become manual. I guarantee this. Fixed sun control elements should not suppress lighting from the sky in cloudy climates, which to me is where we are. Boston's cloudy enough that to me it's a cloudy climate. One solution we've used a lot is things like these Mecco shades. They're perforated shades. You can still see through them. And this table here is a shade with 3% open. Only 3%. They make 3, 5, and you've used this, 8? I don't remember the other. So 3 is doing a lot. And then you can get different colors, and you get different solar transmittance, solar reflectance, solar absorptance, and VLT. So to some extent, a shade that knocks down 90% of the visible light, when the sun is on it, that's plenty of light in the room. 10% of the light when the sun is on the window through that shade is plenty. Now, you don't want really high solar absorptance, or it just gets hot and it's radiating heat to you. That's not good. The better the glass is, and we're mostly using really good glass today, putting it on the inside is not doing a huge amount at excluding heat, right? Because it's come through that glass. It's already sort of inside. The long wave radiation off the shade is going to get mostly bounced back in by the coatings. So inside for cooling load reduction is always a compromise. But you can pick your shades and get sort of what you want depending on where you are and what the job you're trying to do. Almost the best case is externally operable blinds that can retract, because in overcast conditions, they go away. And this is the Kern Center at Hampshire, Brunner Cott, one of the early Living Building Challenge certified buildings. The reason you see them on only some of the glazing is they didn't want to block the glazing that you could open. They still wanted people to be able to open the glass, and they're kick-out awnings mostly. And you can see that the lower ones are closed in full sun, but the upper ones are not closed because they are shading the sun, but that light is still getting in. Do they still work? Will you stop asking stupid questions? So, blinds. Blinds. most American, the standard blinds you might have grown up with in your house, or if you're old, you still have, because you haven't updated your house. Like this building, which hasn't been updated since Daniel Webster stayed here. But you do get, like, where else do you get this giant key? I mean, come on, is this place awesome or what? To be effective for shading, blinds need to be wider than their spacing. And the typical American blind is kind of 1-to-1 aspect ratio, which means that if you want to exclude the sun, you have to close them pretty close. But if the blind blade gets wider relative to the spacing, the shading effect can be done with them being not very closed. They're way effective at keeping the sun out because it hasn't hit the glass yet. And they can be reflective on top to bounce light way into the space. So here's an example of that. People can see out, but the light is going to the ceiling here. Light shelves are another daylighting and solar protection strategy. And here you see a daylighting, side lighting strategy where there's top and bottom glass that is thought of differently. So I can have an external or an internal light shelf here, and the external light shelf will bounce more direct beam sunlight into the room, and it shades the lower window, but it shades that lower window on overcast days too, so it's more biased to a sunny climate, that external light shelf. The internal light shelf will even out levels of light from front to back in the room. It actually suppresses total light. Light shelves actually don't increase the amount of light that is useful in the space, but they make the reduction from away, as you get away from the window, they make that reduction smaller. And Bill Lamb's book has all these little graphics showing you the different test conditions. You can spend a half an hour looking at a page in that book and just learn so much stuff from other people who have already done the work. I think we're getting worse at learning that stuff. And Straub says some of it's in things called books. On a south facade, that internal light shelf can be designed to prevent direct beam lighting from being in people's eyes. And what's great about that is that you don't need any light control on that upper glazing. So this is the Wampanoag Tribal Headquarters, which I did with Bruce Coldham and John Abrams, and you can see that T-shaped glazing assembly there, where the clear story type glazing, the transom glazing, is wider. And there's a shot on the inside. That transom glazing is over a light shelf, and it doesn't need any light control because it never puts beam lighting in anyone's eyes. And
Or on the back.
on the
Cast.
cask. Yeah, on the cask. Thank you, Henri. And so the casements are have manual shading within user control. Now, as you shift the orientation from south, just like with the overhang, the light shelf has to get longer and longer. So this is not a great strategy on the east. I don't mean in the east, because this building is in the east. It's on Martha's Vineyard. I don't want to confuse people. This is a wonderful job of this. This is library at College of the Atlantic. Dan Scully was the architect. And you see sort of the same type of fenestration design. The upper windows, there's more length of them. They're more continuous than the windows that the people have control over. All right, now I'm going to talk about top lighting. Top lighting can be either skylights or it could be roof monitors with vertical glass facing in whatever direction. Skylights might be bringing in more cooling load because they face the sun when it's more directly perpendicular to the glazing. But south-facing roof monitors can shift the cooling load to another time of year. And I actually only once in my life have submitted and had accepted an ACES paper, and it was on this modeling of skylighting with monitors versus skylights. Yes?
Interrupt you, Mark. Starlight, how much of that 1,000 watts per meter squared do you think gets into the home? I mean, just rough.
So Andy's question is, if you've got 1,000 watts per square meter, which you don't have in Florida probably because it's probably like that you get in the desert, but
We get it.
But if you have 1,000 watts per square meter, his question is how much gets in? And that's dependent on the solar heat gain coefficient of the skylight.
Right.
So if you pick a skylight where the SHGC is 30%, then 300 watts per square meter is getting in.
Does that translate into a cooling load to you?
Yeah, it's definitely a cooling load. But the thing about skylights is it's amazing how little you need to do the job. And I'm going to keep going on that.
Here.
There's a very famous building, well, not famous amongst this group because you have to be a real geek in daylighting, that was done in Utah, Johnson Controls building. It was an early, won a lot of awards, passive solar, and that building is presented in writing by Don Watson, who was like the passive solar consultant, and Bill Lamb. They both worked on this building. And Don Watson won with south-facing roof monitors. The building's got rows of south-facing roof monitors. And Bill Lamb shows you seasonally how much light is in that building because he argued for smaller skylights. And so it's fascinating because they're totally opposite in terms of what their goals were and what happened in the building. And Watson, they're both architects actually, so it wasn't like some dumb engineer did it, which is more likely. Watson was wrong. He didn't get the kind of lighting that is the primary need for that building. And they're written up totally differently by same building. Skylights really work well in overcast conditions because typically the brightest part of the sky is the middle part. When it's sunny, skylights are super bright objects and you don't want them to really be in your visual plane and you don't want the work plane to be lit by them. And you have to think carefully about what's the work plane and whether a space has a work plane. And one of the criteria that you can apply is, are people fixed in that location and they're at a desk or at a machine, or can they just move? So they got their laptop and now the sun is on them and 30 minutes later it won't be, and there's another seat they can sit. It's probably okay. So you have to think about how people are using the space. Whoops, did it again. It's nice to have some direct beam light in the space, just not so it's disruptive. Translucent glazing can move light around the space better. It's still a super bright object, so the glare issues are the same. So here's a lobby for a daycare center, South Mountain Company, and this is the lobby, and that direct beam light is fine. Daylighting designer would call this sparkle. In the old days, they used a lot of the halogen lights to kind of do that, but we try not to use halogen anymore. But one of the things I've observed over a long period of time is that architects love to have a splash of glazing in an entry or gathering space, and then those spaces get brighter than the workspaces, offices or classrooms. And the human eye walks into the human walks into those spaces and they feel dark because you just left a 250-foot candle space and you're walking into a space that has plenty of light Might be 50-foot candles, but it feels dark. So you turn the lights on. So I'm always trying to argue with the architects about not doing this so much, because this is just a continuous big ridge skylight, and it's too much. And you notice how all the architectural photos always have the lights on anyway? Why is that? Okay, so this is some of the classroom, this is classroom photos in that daycare center. And these skylights have blackout, motorized blackout because of nap time, which wouldn't be a bad idea for us either, especially the way they feed us here. And my argument is that there's no clear work plane here, and the kids can move around. All right, they have to crawl because they're little, but they can move. So it's okay to have the direct gain kind of skylight here. This is a school where I think it's not so okay. Look at how small the skylights are relative to a, like a 900 square foot classroom. When I built the daylighting model for this school, the physical model, which I'm going to talk about in a bit, I made the roof so I could slide the skylights up and down the model to take my data. And I thought that, well, like, the side lighting will do the outside half and the skylights will do the inside half. It turns out the optimum place for the skylights is almost at the middle of the classroom. They do so much work. Even in, whether it's sunny or cloudy, the skylights do a lot of work, but don't oversize them and you're good. So here's that art barn again. And the client said, this is an art barn. I'm going to hang stuff on the walls. It's going to be moved. I'm going to change stuff out. So the last thing I want in an art type facility, I don't want beam lighting on the art. So this is designed to put light essentially in the middle half of that building, down the central part of that building. You can see it is like 2 feet wide. Now again, the architect wanted way more. I said, no, you can't have way more. You're going to make the building uncomfortable. It's got no space conditioning. And you can see, if you look at the little photo in the lower corner, you can see the cupola. So the client looked at the schematic design and said, this doesn't look like a barn to me. I want it to be a barn. So we had to add a cupola. And the cupola is this beautiful piece of furniture-like timber framing. You know, there's been some dumping on builders here today. Builders are so amazing at what they can do. So this is just this beautiful thing, this beautiful object with north and south glazing. And there's more glazing in that cupola per lineal foot of building than there is in the skylight. And so in the upper left-hand corner, you can see this little detail at DD of the skylight, and you can see my note to Matt Coffey, the architect. Hey, Matt, can you change this framing here? If I get the extra 1.5 inches on each side without changing the skylight, I increase the aperture by 13%. So that's the kind of detail you have to think about. You want to make every square foot of glass work for you. So how do I come up with how big this ridge skylight is? All right, math. The daylight factor is how we express the ratio of light on a horizontal plane indoors to outdoors. So it's a ratio. If I've got 1,000-foot candles outdoors and I've got 100 indoors, that's a 10% daylight factor. 100 divided by 1,000. For my skylights, there's a calculation. This is only multiplication. There's a little division involved later. SFR is simply the area of the skylight divided by the area of the floor area. VLT, we've already, visible light transmittance. WF is the well factor. So what is the skylight? What's below the skylight? How does the light get into the space? Well, typically there's some amount of framing, and the skylight isn't in a infinitely thin roof. You know, the roof is insulated, maybe, and there's some depth to it. And if you have the kind of situation that I've seen in some cases where the skylight actually comes down through shafts in trusses and then shows up at the ceiling plane, that's a big reduction of light because that well is long and skinny. And then the last piece is the coefficient of utilization in the room, which is a pretty typical lighting term. And I kind of ignored it because what I was trying to do here was not bounce light off of the walls and ceilings, but get it to the floor. So I kind of ignored CU in this calculation. And the well factor is how effective the well is at transmitting the light. And so we calculate the well cavity ratio, which has nothing to do with dentists, and the reflectance of those surfaces matters. So here's this little chart, and the well factor is on the left from 0.1 to 1.0, and it's a log chart. And the number of the well cavity ratio is on the horizontal axis, and the 3 lines are for the reflectance of the cavity. Okay, so it's got, the top one is 80, because the well factor is going to be best if the well lining is reflective. So I've got 80, 60, and 40, and you can see 40 is the lowest line. And I argued with the architect about painting just the well white, but in general, in my life, the score is architects 1 billion, Mark 2. So here's the calculation. The daylight factor for this ridge skylight is I have 7% skylight to floor area. I've got a VLT of 56% with this glass. I have a well factor of 63%, and I calculate a daylight factor of 2.6%. And then, because I am a compulsive measurer, I might actually go back with a light meter, and I got about 2.7% in the middle of this building. That's better. That's obviously mutually canceling errors. No one can do this repeatedly, but someone earlier said this, you estimate something's high and something's low and it all works out. That's what happened here. The really interesting thing here is look at it under the cupola. Yeah, so the cupola, the light under the cupola is less than half the light under the ridge skylight.
It's a cupola.
Yes. Is the cupola glazed? Yes. So north and south glass on the cupola. There's not room for east and west glass because of how it sits as a saddle on the ridge. So the north and south glass is not doing the job for me, but it looks more like a barn. So the client was super happy. In big buildings where you have these big atriums, you can have big skylights, and you can totally manipulate the light with moving shades and reflectors. And Andy would say, but is it still working? And as it turns out, that's a great question. There's a building which I think is Harvard Business School that Lamb Partners did with a big skylight and this movable thing. And I was super interested in it, and the person I worked, Bill Lamb was dead. But I was working with Bob Ostin, who was the president of Lamb at the time, and he told me all about this building, and I had to go there, and I talked to the maintenance people, because that's what I do, you know, like, he said, what do you mean, that thing moves? I am not lying. All right, modeling daylight, I'm going to be finishing up. So you can do all this on a computer, and today you can do it way easier on a computer. But one of the cool things about light and daylight is light scales perfectly. Like if you're modeling the drag in a wind tunnel on something and you make a scale model, you have to do all these corrections, right? Or in water for boats. But light is light, it just scales perfectly. When we built daylighting models, we were always careful to do a couple of things. We painted the inside surfaces with the same paint that we were going to spec because we want the same reflectance. And then in the apertures that mattered where the glazing was, we made them scaled to the same thickness. So even though we're using a lot of foam core, we don't want the foam core to look like it's 2 inches thick, and because it's not going to give us the right results. So in some cases, we'd use a piece of foam core and then build up layers to make it represent the actual thickness of the assembly that the glazing's in. So we paint the exterior. And this cool wooden thing is a thing that Bruce and I built to actually be able to swing a model through a true sun path. Because if you just turn it on the horizontal, that's not how the sun works. The sun is not a path like this, it's a path like that. So the fixed angle there, if I remember correctly, is the latitude, and that stays like that. And then you can see this whole thing tilts so we can do winter, summer, equinox measurements. And then that's Sky Snuffles. Sky Snuffles was, RIP, an official member of the Appalachian Mountain Club 4,000-footer peak club. He climbed all 48 of the New Hampshire 4,000-footers. He was a brave-hearted dog. Anyway, so we would build these models, and you can see Bruce messing with the interior of this, and you can see along the north wall here, this little like skylight structure, these offices. So this was Stonyfield Farms, the yogurt people, and the north wall was the party wall to the whole manufacturing production facility, so no glass there. And we actually, this was an amazing thing. It's never happened again in the history of design. We convinced the brass that they didn't need to have their offices on the south wall, which would have completely blocked everybody else's view. And we put them on the north wall, and they bought into that. Amazing. And then what you see here is these light meters. And so we're measuring light on the outside of the model, and we're measuring light inside the model, and we're sliding the light meter down these tracks inside the model. And you got to be quick. You know, one person's writing it down, and reading it, the other person's moving it. And we do this on a sunny day and a cloudy day, so it was very weather dependent. And you can see in the lower left-hand corner, there's this devilishly handsome man with Oakleys, like really fashionable, like back then. And you can see the roof monitors flipped back because we modeled this with roof monitors, and we modeled it with skylights, and skylights with fixed reflectors, all kinds of stuff. This is the thing I wrote the ACES paper on, because we also modeled the heating and cooling load. And we're just testing it and looking at what it looks like inside. So on the right are views inside the daylighting model. And you can see the little offices, and the two different photos are a row of small skylights in the middle of the space, and then skylights at the back, the very back of the building. And on the left-hand side, you can see in real life the effect of those skylights against the white painted wall. And that sunlight never gets to the offices. It never climbs down that wall far enough to be in anyone's view plane or in their offices. It's just this big reflector, and look at the light coming off of that wall in those offices. And then there's an inside view of one of the offices. So we also were fooling with like how much aperture to have in the office. Like it would be too much if the offices were just essentially a glazed roof. So we had to fool a bit with that as well. This work is so much fun. So this is probably the biggest footprint building I've ever worked on. It's a Black Hawk helicopter facility in Vermont, Smith, Alvarez, Sienkiewicz. And you can see the cool model we made. And we're on a roof in Burlington testing this. And you can see the two interior photos are with a roof mask of 2 rows of skylights versus 3 rows of skylights, where the 3 rows of skylights are up against the wall to get that secondary reflection better. And then here we are back to that Forest Society building in New Hampshire, and on the left is the model for the offices. And you can see all the glazing masks that went on there to test that little model and end up with the 2 windows that are pushed against the party walls of the offices. And then on the right, you see the model with what the architect wanted, which was this kind of butterfly set of clear stories. And you have to be gentle. This is a wonderful building. Stu White from Banwell Architects was the architect, and I had to build that roof, even though I knew that roof was going to suck. So we have different roof masks for this, and then we measure it, and then you can show him the difference. And architecture is fundamentally the manipulation of light and space, right? That's kind of what we're trying to do in terms of making how people react to what we design. So anyways, we ended up with a south-facing clear story, because that does something, and 4 skylights. And you can see on the left is the model, and on the right is the building. So we're trying to make the model within reason as close as possible to what we're going to build. I haven't done this in years. No one's asked for it. It's like almost everything else I do. I am obsolete, but that's okay because I ride my bike. Yeah, that's what I have. Joe, I couldn't hear that at all. Does that work? There we go.
Thanks.
Much better.
Philip Agee, Virginia Tech. I've got a compliment and a question. So your slides were probably the most easy to read and appealing to the visual perception of humans because you used contrast. And I know it's MIT colors too, so it's maybe just convenient. But one of your slides had a heading that said reducing contrast as a strategy. So could you just differentiate between environmental contrast, and I think what you meant was the way the light diffuses in the space, versus leveraging contrast and controls and doorknobs and the pieces of the building that people actually have to interact with?
So he's asking me about define contrast, and I'm really just talking about the brightness of objects in your view plane. And we want that gradient to be as gentle as possible. We don't want a black wall, which would only be designed by architects in Denmark. From my experience, they love black, and then a window right in the middle of it. You can't see if you're looking in that direction.
Thank you.
You have the last question.
What's that?
Because I'm buying everybody.
It's a good question, I feel. I might
All right.
have missed this one along the way. I love your model. We've talked a lot about in the northern climates getting solar heat gain to help offset zero energy buildings and using that as an advantage in dormers and such in the summer as cooling. My question, the calculation for daylighting is when your reflection point changes, how is that calculated? And my point is when you get snow on the ground, like in Wisconsin, that changes the aspect outside pretty drastically. And I guess the same example can go for lake reflection of how is that calculated into the formula, because it does change drastically when that happens.
Yeah, so when I used to use way back when we used to use sun code for heating and cooling modeling, which is probably what I used when I did that Stony Field thing, I get to set ground reflectance, right? So I'm setting ground reflectance high in the winter when it used to snow. Maybe it still does in Wisconsin. You guys do curling, right? So you definitely need ice in Wisconsin. And I'd set it at 20% for the other months. So yeah, if you're getting down to that level of specificity, and you know that all your other numbers are right, because remember, for me, anything that's plus or minus 20%, we're golden. Because most of other calculations I look at from people are off by 100 or 200%. We're not worried about the decimal points. But you're absolutely right, in a snowy climate, reflections matters.
Well, within an order of magnitude, that's okay. It's just a decimal point.
Just a decimal point. And they're very small.
Okay, lunch. Round of applause. Thank you, thank you.